Welcome. We are about to examine the architecture of reliability, a look at the invisible logic that governs our most complex systems, from institutions all the way to algorithms.
We operate under a primary assumption that modern systems value talent. This is the belief that exceptional ability is what designates the path to advancement.
A second, related assumption is the primacy of intelligence, the idea that the capacity for complex problem solving is what a system truly values at its core. And a final assumption, of course, is the merit of hard work, the principle that effort is the main driver of recognition. But a deeper analysis reveals a different, more fundamental preference.
You see, above talent, or intelligence, or even effort, systems are architected to reward one thing: predictability. The most important value isn't peak performance, it's consistent performance. This is the central idea we need to explore.
Now, this preference isn't arbitrary at all. It's actually a functional imperative, and it's derived from a system's single most important directive: self-preservation through stability.
So when we talk about predictability in this context, we're not talking about originality. Not at all. It's a measure of reliability. It's simply the degree to which a behavior can be anticipated, which in turn reduces uncertainty for the entire system around it. The logic here is sequential, and it's entirely driven by cost. It works like this. A system's primary mandate is to maintain stability. Any disruption threatens that stability and always comes with a cost. The biggest source of that disruption? Behavioral variability. So, to minimize costs, the system has to select for predictability. The outcome is really just a functional equation. And when you put them side by side, the comparison is pretty stark. Variability introduces complexity. It makes coordination harder, it increases inefficiency, and it drives up costs. Predictability, on the other hand, does the exact opposite. It simplifies coordination, it boosts efficiency, and it reduces costs. For any system that's optimizing for its own survival, the choice is obvious. This preference for predictability also serves another core function. It actually operates as a kind of mechanical substitute for what we would call social trust. Think about it. Consistent behavior establishes a reliable pattern, and that pattern functions as trust, which reduces the need for costly oversight. Monitoring, after all, is a drain on resources. A predictable component within the system minimizes that drain, which increases the overall efficiency of the whole operation. So, given this clear preference, systems naturally evolve mechanisms to secure it. They build reinforcement cycles, specifically designed to select for and then amplify predictable behavior. And these reinforcement mechanisms are everywhere, operating across major domains. In education, things like rigid schedules and standardized tests condition students for consistent, measurable output. In the professional world, reliability signals low risk, so advancement pathways naturally favor consistent individuals. And in technology, algorithms are literally designed to filter for predictable data patterns, treating any variability as just noise to be removed. The result of all this is a closed feedback loop. Predictable behavior is rewarded with opportunities. Those rewards reinforce the behavior, which then becomes an ingrained habit. And that habit, of course, increases predictability, which just starts the cycle all over again. It's a perfect, self-perpetuating selection mechanism. This systemic drive for stability, however, creates an inherent paradox, a deep-seated conflict within the system itself. Here is the fundamental trade-off. Predictability gives you stability, efficiency, and control. But innovation, adaptation, those things are products of variation, of unpredictability. And that variation is, by its very definition, a form of systemic risk. This means that systems will tolerate creativity, but only within very defined, very safe boundaries. As soon as it steps outside those boundaries, it gets reclassified from creativity to risk. The long-term consequence of optimizing too much for predictability is systemic rigidity. A system that has successfully stamped out most of the variation also loses its plasticity. It becomes brittle, and it's increasingly unable to process new threats or adapt to fundamental shifts in its own environment. So, to conclude, the systemic preference for predictability isn't an ideological choice, it's purely functional. It's an architecture designed for one purpose: to minimize uncertainty, reduce cost, and ensure the smooth, continuous operation of the system. And this leads us to a final, critical question.
If systems are built for stability, but survival ultimately depends on adaptation, what happens when the change required is, by its nature, unpredictable?